So, are you able to see the things? Can you
Yes.
see the screen? Okay.
Yes.
Okay.
Yes, sir.
Okay, so let's solve one more question. So it will be a little challenging one, and then once it is done, we will quickly move to the two small topics, uh, which are not that important, but still we will cover them. So let me just uh, solve this question here first, so that you will get more comfortable with how to solve these questions, and then we will move to that topic. So let us say you have, this switch, and this switch is actually closing at time t is equal to 0, and then we have another circuit like this. This is 10 volts and this is 2 ohms, and this is 6 ohms, and then we have an inductor here which is 5 Henry, and we have this current here, right? This current IT, and then again we have a switch like this, and the thing is, this switch will close at time t equal to 4. So in this particular scenario, what you have to do is you have to actually calculate the current IT for time t greater than equal to 0. So you have to get the expression for IT for time t greater than 0. So I'll give you 10 minutes to solve this. A bit challenging question, but it will clear it will clear some of your doubts if they are, once you do this exercise. So I'll give you 10 minutes for this. So right now it's 10:32. So I will get back on 10:40 and I will ask you this, and then we will solve this. Okay? Any doubts here related to this question? Okay. So solve this and let me know whether you are able to do it or not. Okay, then I will solve this question because I could have waited more, but problem is, so I will discuss this question. Okay. So here basically we will have three different cases. The first case is basically t less than 0, and then we will have t in between 0 and 4, and then we will have a t greater than or equal to 4. So this is the situation in 0.34. No, it's not 0.34. Okay, so in t less than 0, all of you will agree that only this switch will be there, right? This will be there, and there will be this switch will not be there. So for t basically from minus infinity to 0, the circuit is in steady state. So what will be the inductance state? Will it be short or open?
Sir, but switch is not even closed, no? T minus infinity to 0. No, sir,
It is short.
Oh, yeah, sorry. So basically, at time t from minus infinity to 0 also, if switch is open, let us say, then also what will be the value of, what will be the state of inductor?
It is short.
It will be short, right?
Not
So it is, so what will be the current flowing in it?
zero.
Zero. And you know that the same situation will happen at I of 0 plus also, right? So you have to keep this in mind, because this is the boundary condition for the inductor. So from this situation, from this minus infinity to 0, you got this information. Okay, and you know that from minus infinity to 0, both the switches are off. So now things come like, when you are in between 0 to 4. So in 0 to 4 situation, where your time is between 0 to 4, what will happen in that case? Let me copy this here. So here, if this closes up, if this closed, this will be closed, and this is still open, right? This is still open. So now if I say I want to know the current in this 5 Henry at infinity
So
interval.
it will be 4 into 1 minus e raised to minus 2t.
Yeah, that is the final answer, right? Good. But right now I want to ask the students, like if I want to calculate I infinity here, actually, I will tell you more details about it in a while, but let me know what this value will be here in this situation.
4 ampere.
4 amperes.
4 ampere.
And the reason for that is, inductor is short circuited, and when the inductor is short circuited, the current is 40 divided by 4 plus 6, and that is 4 ampere current flowing. So can anyone answer me this, that we were considering these intervals, right? One is from minus infinity to 0, we already studied that, and then we moved to time t is equal to 0 to 4 situation. At time t is equal to 0 to 4 situation, how can I say that it's I infinity? I infinity means we are going beyond this time limit, right? We are actually going past infinity here, right or not? So why I am writing this as I infinity?
Sir, because after right now it would be infinity only. It would attain stable, the steady state after pi tau.
Good, very good.
When we second switch after t equals to 4 seconds, sir,
Right.
then we would superimpose it.
No, but the first person who told me this answer is correct. If you see this particular situation, when you are at this point, when this is closed and this is open, at this situation, what is the Thevenin resistance across this inductor? What is the Thevenin?
10 ohm.
The Thevenin resistance is 10 ohms, right? So what is the time constant here for the inductor case?
2.
e raised to minus
No, it will be 2.5.
2 point.
L by R नहीं होता क्या?
yes, sir, that's
Yes.
only
0.5. Sorry.
0.5.
It will be 0.5, right? So the thing is, it is 0.5, right? So we know that all the transients will settle down after phi tau. पता है ना? We know that or not? So that means it's 2.5 seconds, right? Right? So this means on this axis, after 2.5 seconds, if there are any transients, it will settle down and it will be a constant value after that. So that means after 2.5 seconds, we are actually, heading towards the steady state. So that's why we wrote infinity here, just for the simplistic understanding, but actually it is I at, somewhere, like I can write it as, but actually it is, practically speaking, it is infinity only, because this is basically, a settling point where the current settles down. So if you write I 2.5 or anything like 3.5, then also it will be, a settling value only here. Okay. So that settling current, we have already evaluated it, and its value is 4 amperes. So normally we write it as I infinity, just to, correlate with the equation which we had derived for the inductor, which is ILT is nothing but I infinity plus I0 minus I infinity e to the power minus t by tau. So if you calculate this, I infinity, it's 4 amperes, and then I0, it's already 0, and then I infinity is again 4, and then you have e to the power minus t by tau, and tau you have already calculated it as 0.5. So this will come out to be 1 minus e to the power minus 2t amperes. So this is the current that you will have in between 0 to 4 time limit. Okay. And if you want to write it in terms of the unit step function, how will you write it? If I want to write it in terms of unit step, how will you write it?
ut minus 4. We will multiply.
ut minus 4.
Yes, sir.
Right. You can write it like this. So this thing will go away and it is incorporated in this. Okay, now what will happen is, like, we are heading towards t greater than 4 situation. In t greater than 4 situation, what will happen?
That
In t greater than 4, what will happen?
दोनों switch close हो जाएगी.
both switch will be closed.
Both switches will close, right? So at t greater than 4, both switches will close. So now we will see what we will again write. We will again write the I infinity and I zeros for this inductor. Okay, so now what will happen is, the moment this switch closes, the second one, and the second switch closes at time t equal to 4. So if I want to calculate the initial current which is flowing in this inductor, how will I do it? I will use this equation which is on the top,
Equation.
the first equation that we have derived it, right? So we can use it to get the value of current at 4 minus. We can get the current at 4 minus, and that is nothing but 1 minus e to the power minus 2 times 4 here. So this is roughly equal to 4 amperes only. So at 4 minus means just before 4 minus, this will be the current equation which we have derived. So we will use it for calculating this, and its answer is roughly approximately 4 amperes. That is nothing but I at 4 plus. So this is the one. And for infinity, at infinity state, what can you do now for infinity state? What is the state of the inductor at infinity?
Short circuit. Short circuit.
So we can replace it by short circuit here. And then what we will do is, we will use nodal analysis to calculate the,
That is 30.
what is the value of voltage here?
7.
30 by 11, right?
Yes, sir.
No, the voltage will be, sorry.
Current आएगा voltage 180 by 11.
Right. So the voltage is 180 by 11, and the current which will flow here is nothing but, it's at infinity, and its value will be 180 divided by 11 times 6. So that will come out to 2.727. This is the current that you will get. What is the Thevenin resistance? What is the Thevenin resistance in this situation across the inductor?
22 by 3.
Just a second. Yes, very good. So Thevenin resistance is nothing but, you short circuit this voltage, and you want to check across this point, right? What is the resistance? So that resistance is nothing but 4 parallel with 2 and then in series with 6. So 4 parallel with 2 and that is in series with 6. So answer is 22 by 3 ohms. So the corresponding tau you can calculate as L by RTH, and this RTH is now with this 22 by 3, and this comes out to be 15 by 22 seconds. So the current IT, then you can write it as I infinity plus I at 4 plus minus not 4 plus, 4 minus I infinity, and then e to the power minus t by tau. I infinity current, you have calculated it already, it's 2.727. Then you can use this I4 minus 1 which is given over here, this current which is 4 amperes. So once you put this value, this is 4 minus 2.727 e to the power minus t by tau. One mistake I have made.
T minus 4.
Right, very good.
Right, sir.
Yeah, this is the mistake. So it's t minus 4 now, because the switching action is now taking at after 4. So I have given you this generalized expression, if you remember. So it is like this. So if you want to write the complete expression for IT, it will be actually 0 for t less than 0, 4 1 minus e to the power minus 2t for t in between 0 and 4, and for t greater than or equal to 4, it is 2.727 plus 1.273 e to the power minus 1.4667 times t minus 4. So this is basically the current expressions. So in this question actually what we wanted to ask you is that the current IT at time t is equal to 2 and at time t is equal to 5. So this was the question, like find IT for time t equal to 2 and time t equal to 5. So what you have to do is, for calculating time t at time t equal to 2, you will use this expression for time t equal to 2. For time t equal to 5, you will use this expression to calculate the current. Okay. Any questions here? So with this, I have covered most of the variations that you can have for transient cases. So practice these questions. The more you will practice, the more comfortable you will become in these type of questions. Okay. So today I am stopping it here, and from now we will head towards the second part of this. Not second, it's like these two topics which I will be covering are very brief. We will not go into the details of that because they are not that trivial, but still we want to cover it for the sake of completeness of this course. So let me give you a brief idea about today's topic. So the topic which we will be going to discuss today is called as filters. Okay. So what are filters basically? Filters are, they are type of a device which tries to, filter out something from the input. So for example, in real life situation, if I give you this example of tea making process, then you know that there will be some tea leaves which will be floating around in the mixture. So you will be using filter to filter out the tea leaves, right or not? Right or not? In this particular situation, what you will do is you will use filters to filter out the tea, and the main component, which is tea, will be in the separate cup, and the garbage which you do not require, you will filter it out and throw it into the dustbin. So this is basically a typical example of filter. In case of electronics area also, we have the concept of filters. And what we try to do in this situation is, let us say you have three frequencies: cos omega 1t, cos omega 2t, cos omega 3t. So let us say you have these three frequencies, cos frequencies, which are actually summed up together, and it's giving you some complex signal. Okay, it is because once you sum them up, and if you write a single cos function of this particular summation, which will have omega t plus phi, some expression will be there. So what will happen is, this particular function, sorry, not this one. It will not be possible to actually make them combine together into a single, because you have different frequencies here. Here you have omega 1, omega 2, omega 3. So all of them have different frequencies. So you cannot combine them into a single function. So what happens is, this particular cosine functions, if you try to add them together, what will happen is, you will get some waveform which looks like this, something like this. Just giving you a random idea like what filters are and what we are trying to do here. So this particular waveform which we have here, so what happens is, sometimes there is an applications in which, if we want to remove one of the components, let us say omega 1t here, then how we have to do it? Like, what is the way we can do to remove this omega 1t cos omega 1t sinusoidal cosine signal? For example, if I create a device in which, if I pass this waveform, then it should give me output as cos omega 2t plus cos omega 3t. And note that on the frequency scale, omega 1 is here, omega 2 is here, and omega 3 is here. So increasing order, the value of omega 1, omega 2, omega 3 is given in this fashion. So actually omega 1 is less than, omega 2 is less than omega 3. So in some situations, what happens is, we want to remove this omega 1t, we want to only keep omega 2t and omega 3t. So in these type of situations where we want to remove this one and retain these two, these type of devices are called as low pass filter. In short, we call them as LPF, but it is called as low pass filter. So why it is called as low pass? It is called as low pass because it is passing the low frequencies. I told you wrong way. It's a let me do not confuse you here. So what happens is, if I want to actually remove these two components and retain only this component, let us say that if I want to retain only this component and remove these two, so if we know this device, then it will be cos omega 1t. So cos omega 1t will be the only answer. And what will happen is, this complex signal which looks like this and which is a combination of these three cosines, once it passes through this device, it will give you cos omega 1t, and you know the sign, variation of this signal. So this type of devices which actually allow low frequency signals and stop the high frequency signals, these type of filters are called as low pass filters. Low pass filters. And low pass is coming because it is passing the low frequency and removing the higher frequencies. So here you see on the omega axis also, I have kept omega 1 this side, omega 2 this side, omega 3 this side. So let us now if we assume that there is one frequency, let us say critical frequency, which we are calling as WC. So what we are saying is, everything below WC it will pass, and everything after WC it will reject. So these type of filters are called as low pass filters. And if I want to draw the characteristics of this filter, it looks like this. So you do V out by V in. You take the transfer function. You take the transfer function of the circuit. Basically, you already know how to calculate V out by V in. So once you do a V out by V in, and if you vary the frequency, then what will happen is, it looks like this. The characteristics of this looks like this. So what it says is that after a specific value of omega c, so let us say you have these three frequencies like this. So what it says is, it will, whatever frequency you have at omega 1, it will be passed uninterrupted. So the value here is 1. So that means you were passing here cos omega 1t, right? So cos omega 1t will be passed uninterrupted because the gain is 1. So if your input is cos omega 1t, if the gain is 1, then what will happen is, the output will be same as V in or not, because this is the gain value, V out by V in. So V out by V in is 1, and your V in is cos omega 1t. So V out will be cos omega 1t. As you can see, omega 1 is having a gain of 1. But now when you are passing cos omega 2t here in this circuit, whatever hypothetical circuit we have here, what will happen is, this is the characteristics of this circuit, and you can see at omega 2, what is the gain at omega 2? What will be the gain? So at omega 2 we have 0 value, right? That means V out by V in is 0. So when you put V in as cos omega 2t and you multiply this side, your V out will become 0. Similarly, for omega 3 also it will be 0. So what we do is, we try to develop some circuits which looks like this, like this. So all the circuits which looks like this, having this characteristics for the gain, because this is a gain actually. So the voltage by V in, V out by V in is also called as gain. So all the circuits which behave like this are called as low pass filters. Okay, so any questions here related to this? Okay, so let us say if I want to retain omega 3, if I let us say want to retain only omega 3, then what will happen?
High pass. So we can have some high pass filter which can means allow only above some
Right.
At that time, the
decided frequency.
omega 1 and omega 2 will be 0.
Right. So what will happen is, just a second, huh? I will just see that figures. Just a minute. Okay. So now, as you told me, like if I want to pass only omega 3, so what will be the circuit? How will the circuit look like? Circuit will look like this. You have omega here, then you have omega 1, then you have omega, then you have, let us say not this here, then you have omega 2 here, then you have omega 3 here, and now you will have a omega C here, let us say. So what will happen is, your filter should look like this. Right or not? Because at this omega 3, you will get the gain of 1, and for the other ones you will be 0 gain. So this, yes.
So it will pass only the frequencies which are lesser than omega.
It will pass the frequencies which are greater than omega C, not lesser. Okay?
LPF, okay sir.
On omega, on this side it will pass all the frequencies which are less than omega C, and it will remove all the frequencies which are greater than omega C. Okay? Okay. So now let us say if I want to retain only omega 2, if I want to retain only omega 2, so what will be the characteristics of that filter will be? If I want
Something like pulse like shape. Yes, sir. You should have book omega C type values.
good. So let us say you have some omega C dash here and omega C double dash here. So it will look like this. So it will be 0 here. Only omega 2 will be passed, and then it will be all again 0. So these type of filters are called as band pass filters. Band pass filters. Why it is called as band pass? Because actually it passes a band of frequencies in between the continuous frequencies. So in the continuous frequencies, this frequency, this part is gone, this part is gone, only a specific band is passed. That's why it is called as band pass filters. Okay. Now another situation is that it might be the case that I only want cos omega 1t and cos omega 3t. Then what will happen?
तो सर ये आपने बैंड पास फिल्टर के ऊपर जो बना है वो हाई पास फिल्टर
That is high pass filter. Yes, it is high pass filter, or it's in short called as HPF. So if I want to retain only omega 1 and omega 3 and reject omega 2, what will happen in that case?
सर वहाँ पे ओमेगा सी डैश से पहले और ओमेगा सी डबल डैश के बाद होना चाहिए, मतलब वो बीच का वाला डिलीट कर देगा.
Right. So this is basically here, you know, the characteristics will look like this. So it will pass all the values of omega 1 with the value of 1, and it will reject a band of frequencies in between this. It will reject a band of frequencies in between this, and it will pass all the frequencies except in this band. So these type of filters are called as band reject filters. Band reject filters, BRF. So let us try to, you know, see which kind of filters will have these type of characteristics which I have shown you here. So keep these characteristics in mind, and let me show you some filters which can actually, if you try to see, if you want to see like, which kind of filters they are, we will just, cross check it by checking these characteristics. So let me draw this particular circuit here. So let us say you have this circuit R L C. So anything which involves R, L and C, they are also called as passive circuits. Okay, and anything which involves op amps, along with RLC connected to that op amp, that doesn't matter, but anything which involves op amp, they are called as active circuits. Do not go into the details of this, I don't want to go into it, but remember that anything which involves R, L and C, we call them as passive circuits. Passive you know already, but for active I do not want to go more into it. But remember that if op amps are there, then operational amplifiers are there, then they are called as active circuits. So in this particular case, if I want to calculate V out here, j omega, and then this is V in j omega. So if I want to calculate this, I think it's very easy, right? This is the impedance 1 by j omega c here. For the inductance it is j omega L. So if I want to calculate V out j omega, it will be nothing but 1 by j omega c upon 1 by j omega c plus R plus j omega L. Will it be or not? It will be V in here. ये होगा? Just simple voltage division only, right? So there is nothing fancy here. This is simply the voltage division that you will do here, right? So in this case, if I simplify this, I am not doing this simplification, you can do it yourself. And what I am trying to say in terms of simplification means you multiply this to this side, and you bring this into the numerator and cancel this j omega c with this j omega c. So once you simplify the terms, what you will get is this as the answer: 1 by LC divided by 1 by LC minus omega square plus j omega R by L. This is an exercise for you. You can do yourself also. So it's very simple, just adjustment of the complex numbers. So there is no, there is no hard and rocket science here. So it's just manipulation of the numbers. Let me know in case if you do not get this answer in the next class, but it's very simple. Okay. So now if I want to check whether this is a low pass and high pass, what I will do is I will put two conditions here. So once omega is 0, what will be the answer? Because this is the gain, right? This is the gain, V out by V in. So if I put omega is equal to 0, what will be the gain?
1.
1 or not? And if I put omega as infinity, what will be the gain?
0.
So what is this filter? What is this filter doing?
Low pass.
It's a low pass filter or not? Because at omega equal to 0, its value is 1, and at omega is equal to infinity, its value is 0. That means in between it is doing something like this or not? It is going down or not?
Yes.
So that means as the frequency goes, its profile looks like this, and this is the low pass filter because it is passing certain frequencies. Let us say omega c dash here, it is passing certain frequencies with a gain of, let us say, 1 or close to 1, that is close to 0.887. So we are not going into the details of it, but just to tell you that in this region the gain is high, and after that the gain reduces drastically, and it's a complete these frequencies will be reduced value, though you will not get exactly 0 because it's a practical circuit. the curve which I have drawn here are ideal curves. Actually, these curves are ideal, and it never happens in real life like this. The curves look like this. This is the real curve, and this is the ideal situation. And world is not ideal, right? Situations are more real rather than ideal. So here also the curve will look like this. Here also the curve will look like this. And in this case, curves will look like this, and not the ideal situations. So this is basically the low pass filter, because its behavior looks like ideal behavior with this type of characteristics. Okay, any questions here? Okay, so if there are no questions, we can move to another circuit. So let me draw this circuit here. V in, just the placements of resistance and inductance, and you are getting different type of filters.
Sir,
Yes.
sir, you told that this is the ideal curve. Means which one? The one that is smooth one, or the one
No.
that is
This is the ideal one. Because you see, it's a square, right? Complete square. So normally this type of situation never happens. This type of situation will happen, right?
realistic one, the other one, the one that is smooth.
Yeah,
is what
smooth one.
actually happens,
Yeah,
right?
yeah. This is the one which actually happens. And if you want to cross check through the transient analysis situation which we were discussing, you can see from here also, right? If your omega is 0, what will be the impedance of the capacitor when omega is 0? What will be the impedance? Will it be open circuit or closed circuit?
It will be open circuit.
Open circuit, right? So it's open circuit means all the voltage which is over here will come out here, because there will be no current flowing. It's an open circuit. So whatever voltage you will get here is the same voltage which is here. So that means you will get V in j omega. And what happens when omega tends to infinity? At that point, what will happen is, it is a short circuit. Will it be short circuit or not? So if it's a short circuit, this is ground, this is ground, so everything is ground, so this is 0, right? So you can see you are going from V1 to 0 as so this is a second way of thinking the same thing. Okay, in this case, the one which I am showing over here, if I write omega equal to 0, what will be the state of the inductor? Will it be open or closed?
Lower.
It will be short circuit or not? Because we know it is j omega L, right? So when omega is 0, the j omega L is 0, that means it's a short circuit. And if omega is infinity, what will happen? What will be the state of? Will it be open circuit?
Yes, sir.
Yes, sir.
So if it is open circuit, means whatever voltage you have here, the same voltage will appear from here to here, right? Because there is no current flowing. So if that is the case, at infinity you are getting V in, and at 0 you are getting a 0 voltage across the inductor. So that means you have a characteristics that looks like this, because at omega equal to 0, the gain is 0, and at omega is equal to at infinite point, the gain is V out. It will be actually the same as V in, because this inductor will be a open circuit. And if you want to cross verify this with the expression, then you can write V out j omega by V in j omega as j omega L divided by R plus j omega L plus 1 by j omega C. So this is simply the voltage division across the inductor. So if you simplify this, what you will get as the answer is, again, an exercise for you. It will give you this answer. This is the answer that you will get once you solve this complex number. And by complex number solving means you just simply multiply here and bring it in the numerator, and whatever answer you will get is this. And the important thing is you just normalize it and see whether you are getting the same answer or not. So it's very easy, there is no rocket science here. So from here, if I want to put omega equal to 0, what will be the answer for the gain?
0.
0, right? And for omega equal to infinity, if I put, what will be the answer?
1.
Okay. So from here also you can check by writing this expression, or by intuitively also you can check without calculation also, if it is a simple circuit. If it's a complex circuit, then you have to draw this transfer function, and from here you can put omega equal to 0 and omega infinity points and check whether what answer you are getting. Okay, let me do one more here. So let us say you have this circuit. Like this. Only the adjustments. Sorry?
Sir, this is high pass filter?
This one is high pass filter, yeah. This one. This is high pass filter.
Sir, 1 minute, can you show graph?
Yeah, this is the one.
Okay.
So in the band pass filter, what happens now is, see here we cannot analyze whether it's a band pass filter or not, because it's not intuitive, because you can see R will remain there even when omega is 0 or omega is infinity. So we do not know like how to analyze it for band pass. So in this case there is no other option rather than drawing the rather than solving this for the transfer function. So if you solve it for the transfer function, then what you will get is this as the answer. And then if you solve it further, then what we will get is R by L j omega divided by R by L j omega plus 1 by LC minus omega square. So you will get this answer. So here you can tell what is the value of omega 0. At omega equal to 0, what will be the answer?
0.
0.
And how about at omega equal to infinity, what will be the answer?
Again 0.
So what can you think about it? Like, at omega equal to 0 also it's 0, omega equal to infinity also 0. That means somewhere in between it will be close to 1 or not?
Yes, sir.
So if you remember, then the characteristics of that will become like this: V out j omega over V in j omega, and this is your frequency. And after this is omega is equal to 0, and this is omega equal to infinity, and somewhere in between it will rise and then it will fall again. So this type of circuit is band pass filter, because it is passing.
Sir, we can
Yes.
say now that omega must be 1 by root LC to be 1.
Why you want to say that?
Because omega minus 1 by LC equals 0, so it to 1.
Omega equal to 1 by root LC is what? Like,
Sir, the frequency is V in by V out equals to 1.
Means
okay.
voltage gain equals to 1.
Sir,
Yeah.
calculate this in,
Yeah.
like
Yes.
omega by root square.
Right. Yeah, at omega equal to 1 by root LC, that means you are here. Good. So this is basically at this point you are getting exactly 1, right? Okay. So this is band pass filter, and in case if you want to do another one, which is the band reject filter, then it will be like this. You have R, then you have L here, and then you have C this side. So in this way you have band reject filter, but right now the voltage that we will take here, not at the end. So this is the voltage here which we are taking this side. So in this case, when you calculate the voltage output or you can say VO j omega, it will be nothing but j omega L plus 1 by j omega C divided by R plus j omega L plus 1 by j omega C. Right or not? Because right now you are calculating voltage across the series combination of L and C, right? So that's why you have on top this one. So again, an exercise for you. If you solve this, you will get 1 by LC minus omega square divided by 1 by LC minus omega square plus JR by L omega. This is your VO j omega by V in j omega. Now again, if you put omega equal to 0, what is the answer?
1.
And when you put omega equal to infinity, what is the answer? 1 or 0?
Sir, 1 because
Sir,
it is
one.
fine.
Right? So what is this situation where you have low frequencies passing, high frequencies passing, but somewhere it will reject in between or not? So,
Yes, sir. At 1 by root LC. We read that.
yeah, same thing. So basically, again you have gain here, which I am writing as AV. So that means you have something like this, and this happens at 1 by root LC, and here you are getting 1 gain, and it's passing all the frequencies which are here, as well as it is passing all the frequencies which are here. So these circuits which I have shown you, they are all passive circuits. Why they are called as passive circuits? They are called as passive circuits because they do not have op amps here. So if op amps are there, then also you can actually solve the same thing, and solve the same thing means, let us say, I'll give you one exercise. In the next lecture we will discuss this. So what I am claiming here is that this circuit is a low pass filter. So if this is the circuit, and I think you can solve this because there is no concept required here, just nodal analysis and KCL and KVL. You have already solved this so many times in your earlier lectures when we were doing op amp. So here you have, let us say, this as C, and then you have here R, then you have R here, and then you have a capacitor like this. Okay, so let us say both of them are having same capacitor. Let us say the values of both of them are C only, and all these are same R except this one. Okay, so now this is your V in, this is your V out j omega, this is V in j omega. So now my claim is that this particular circuit, if you calculate V out by V in, you will get a low pass filter characteristics. So in the next class, you calculate the transfer function, solve it, and let me know what answer you get, and you prove it that it's a low pass filter. Okay, and these type of circuits which involve operational amplifiers in it, they are called as active filters. Active filters. Earlier ones are called as passive filters. Okay, so today's class is over. In the next class, and this topic is also over, I will cover a very brief other filters also which involves operational amplifier, but it will not require anything extra knowledge rather than only solving it through nodal analysis, which you are comfortable already. So use the concepts of nodal analysis, try to calculate this gain, and use the concept of omega 0 and omega infinity situations, and check whether this is a low pass filter or not, and try to solve similar questions from book related to filter design. So this is the only thing which we wanted to cover for filters. In the next class, I will discuss one more small topic, which is transformers. Then we will finish off this class after that. Any questions here related to this particular topic? So are you able to get to this? Sorry? Can you? Yeah.
No, sir.
Okay. So I think you must have, so you got this topic, right? So if there are questions, please let me know.
Sir, there is a and then give like how much syllabus is left now?
No, after this only one topic, very small topic is left. So this is also basically, if you see this topic which I have covered, this is nothing but you have to calculate V out by V in only. So other thing that was required was to check for omega 0, omega infinity. So just to give you a brief idea about filters. The next topic is also like that. It's very trivial, so it will not be